honor for us to invite the Professor Wang Liqiu from the Hong Kong Polytechnic University. I know that a lot of the students and the teachers know him very well. But firstly, let me give a brief introduction to the Professor Wang. Professor Wang holds the Otto Kuhn Charitable Foundation and endowed the professor in smart and sustainable energy, and is the chair professor of the thermal fluid and energy engineering at the Hong Kong Polytechnic University. He also served as a director of the PolyU Zibo Technology and Innovation Research Institute. With over 3 decades of research at the crossroads of the thermal fluid science, biomedical engineering, micro and nanotechnology, energy systems, and advanced manufacturing, Professor Wang is a truly interdisciplinary pioneer. His prolific output includes more than 590 peer-reviewed papers, among which over 60 appear in top-tier journals such as Nature, Science, PNAS, Physical Review Letter. He is also author of the 11 scholarly books and holds over 40 granted patents. So today, his lecture title is Nanoliter Droplets, Generation, Manipulation, and Application. So let's welcome Professor Wang.
Thank you, Professor John. Good morning, good afternoon, good evening, depending. Okay. Today I did bring some souvenir from PolyU for you, but only for those of you attend this talk in person in particular. After my talk, if you have a question, if you ask a question, you can pick up any two over there. If you didn't ask me questions, just pick up one over there. I believe I bring enough for all of you with a small souvenir from my department. If you love PolyU, please use this opportunity to get something for you. So the topic called nanoliter droplets. Mainly, I will discuss generation, control, and some applications of those kind of small droplets. How small we can call droplets as nanoliter droplets, then basically roughly 1 nanometer equal 1/5,000 of blood amount in 1 mosquito bite. So very small. I need to wait. Go to next slide. First of all, I would like to thank this talk organizer, the Xi'an Jiaotong University, for this opportunity to discuss some of our research with you. Second, I'd like to thank RGC, that's Research Grant Council of Hong Kong, for constant support. Research in my group normally are called many eating kind of activities. Then I thank my team. So today, all the material by my former team members over here, I show roughly 50 of them. They did this PhD with me in last 10 years. Also, some did this postdocs in my group. Then also, last but not least, all of you for attending this talk. So why worry about this very small or tiny amount of liquid? Because those kind of nanoliter droplets can find applications in many fields over here. I just list some of them. In particular, today I will talk about use those kind of droplets for soft manufacture. Somehow some videos not play automatically, so it doesn't matter. Just believe me, okay? We can use those kind of droplets for manufacture something, but we use liquid. That's why we call the soft manufacture. We can produce some products that can be used for, food for the baby, also for biomedical applications for detection, drug delivery, etc. But I believe all of you know to generate a job is very easy. If you turn, type letter Y's, then you can just not so strongly you can generate a joblet. But those kind of joblet generated by our hand, normally the size very big. The size distribution not so uniform, not so well controlled. So that's why, we need to use another technology, mainly we call the microfluidics technology to generate those kind of a tiny amount of liquid droplets. In this field, people mainly worry about, droplets size, droplets distribution, droplets generation. Generation means sometimes we wish our generation as fast as possible. Sometimes we wish to generate one droplet, for example, at 10 o'clock, then stop. Okay, then we generate another 2 droplets at 11 o'clock. So we need those kind of abilities. Then we need worry about the structure of droplets. Although droplets are already very small, but we sometimes we should put into some even smaller material, either gas, liquid, or solid material into this small droplets, right? For example, for drug delivery, we need to put different drugs into this small droplets. Then we need to worry about how to control all those kind of droplets, because it's so small, we cannot use our hand to control those kind of droplets. So for the people working on nanoliter droplets, we need to worry about the size distribution, generation rate, structure, and the way to control, let's say, to move or to merge two different droplets, etc. So over last 20 years, many groups around the world did, comprehensive study or development to resolve all those kind of issues. Finally, up to today, people know how to generate those kind of tiny amount of droplets with a controllable way. Then we just let 2 liquid meet together. These 2 liquid not like with each other, meaning dislike with each other. For example, oil and water, they dislike with each other. Then you let them to meet together. Then you can generate some kind of fluid instability. That's in academic term. In engineering term, if you let them meet together, they will fight with each other. because they dislike with each other. This fight process will give us a flow pattern, which we call droplets, right? So what kind of a method we can let, these two dislike liquid meet together? Then since we need to generate nanoliter droplets, we need to use macro channels, because if your diameter is a macro range, then volume will be nanoliter, right? So then people propose some typical ways showing over here, the simple way, just two tubes, right? Then one float going over here, another float going over here, they fight with each other, then generate droplets. Then at least some typical, the ways or systems or macrofluidics channels or chips to let two flows meet together. Then after last 20 years, comprehensive study by many different groups, basically people already found we have 5 fundamental fluid instabilities. In engineering science, 5 different ways to fight with each other between these two fluids. One is called squeezing, the way to generate droplets by squeezing. Normally, the droplet size, relatively speaking, relative to the other way to generate droplets bigger. Also, size uniformity, not so good. You can see on the top video over there. The second one called dripping. That with this mode of generation of droplets, you can generate, relatively speaking, smaller droplets, and the droplet size quite uniform. If you wish, generate small droplets and the size quite uniform, try to use this way to generate droplets. Third one called dripping. The dripping one is also, the very good one to generate small and uniform droplets. That's the second one. Maybe I mix up, okay? The third one is the jetting. Jetting is another way to generate droplets. For jetting, for the inertial stage, no droplets, just a stream of liquid over there, but this liquid layer will become unstable such that you got droplets in the later stage. This length of inertial stage you can control. Sometimes we wish this length as long as possible. Suppose you use this system to generate fibers, then you wish this phase as long as possible. But if you use this way to generate droplets, finally you wish to generate particles, then you need this stage as shorter as possible. The fourth way to generate droplets called tape streaming. You can see for this one, you can generate very tiny, droplets. Also, generation frequency very high, hard to see, right? Very quickly to generate a lot of small, droplets. Last one, the fifth one, actually proposed, found by my group, called tape multi-breaking ways to generate droplets. For this last mode or last instability, we generate a group of droplets periodically. Then within this group, we can have many or any number of different droplets, but we generate a group by group periodically. Within one group, you can control number of droplets inside this group, you can control size distribution among all the droplets in this group. Suppose you wish to generate a big one first, then small one, then a big one again, or all droplets with the same size, then this mode of instability can help us to do that. Basically, you need to control your flow parameter, liquid properties, or your channel geometrical diameters. So far, people already know we have these 5 different ways to generate droplets. Which way you like, you need to first decide. Then you play around for 3 different kind of parameters to get your preferred way to generate droplets. So I will briefly outline what's that 3 ways. The first one just change dynamic parameters for flow process. Dynamic parameters is nothing more than flow rate or the pressure you add on to push your liquid into your droplets. You just change flow rate, for example. What kind of a method we can change flow rate? We have many, right? The simple one is the valve, right? I put somewhere this valve. If you open valve, then flow rate will increase. If you close a little bit, your flow rate will decrease, right? That's simple way. Another way, you just use a laser shine on your, channel. Then if you got a laser shine on your channel, you hit your channel, then channel cross section will change. Then you can change flow rate, right? Basically, fundamental principle similar as this mechanical valve, right? You just replace your hand then by laser, right? Then we can have the other ways, at least some typical ways proposed in literature to change flow rate. Another way, just put oscillator over there. Then you let your inlet channel oscillate. Then you can change your flow rate or pressure inside your microfluidics system. Over here, maybe I show you this simple approach, mechanical vibrator to vibrate your channel such that you change flow rate of liquid into your system. Looks very simple, right? But we learned this from our beloved dog, right? Our dog use those kind of simple mechanical activities to control generation of droplets from his or her surface, right? That if you use this simple, mechanical ways, we found a very important feature for engineering applications. We found a certain range of vibration frequency. If we're talking about, vibration, we need to talk about amplitude of vibration and the frequency, right? Then you can change your frequency of vibration very easily, right? If you have this vibrator. Then we found, in certain range of this frequency, this red one over here, we found we can decouple generation rate of liquid and the droplets size. Because in this range, generation rate of droplets is exactly same as your vibrator vibration frequency. Then you can, fix this frequency, then fix generation rate of your droplets. How to control the droplets size Then if you open this pump a little bit to a bigger capacity, then you have a large flow rate, but the generation frequency fixed, then your droplet size will be bigger. Otherwise, your droplet size will be smaller. So normally, by macrofluidics system, the size and the frequency coupling with each other. But after you add this simple mechanical vibrator, then you can decouple these two such that engineer very happy about this feature. Then another way to change, flow rate, then you just add another, kind of a force field. For example, you can add electrical field, magnetic field, or pressure inside your, chips of your float very easily. So basically, that's one way to control your generation of droplets. If you wish to get a small one, you do something by, those kind of method. If you wish, droplets are very uniform, you can also use those kind of method to achieve. The second way we can use to control our droplets generation, that's just fluid property. You can use a different liquid right inside your system. That's normally, let's say you change, your liquid to oil. Then fluid property change, the way you generate droplets will be changed. Normally, people use that method, but sometimes we don't wish to change our liquid itself. Then how to change liquid properties? Then we have the other ways. For example, over here, I list some typical ways used in the literature. Maybe I just use this first one as an example. Why not put some nanoparticles inside, let's say, your water, that's your liquid, but distribution of those kind of nanoparticles inside the water will be response to your external, let's say, electrical field. If you don't have electrical field, then all those particles uniformly distribute inside your water. Then you got equivalent viscosity value for your liquid with your nanoparticles in. Then suppose you down some, electrical field, then those kind of particles, the distribution become those kind of configuration inside your liquid. Then you got another value of equivalent of viscosity of your water with this type of nanoparticles inside, right? The third one, maybe if you enhance your electrical field further, then your distribution of particle inside your water become to this pattern. You got another value of viscosity. So you can change your viscosity, for example, by use this kind of method instead of change liquid itself. Then at least some, the typical, method to change your fluid properties, not just the viscosity. You can change the other properties, thermal conductivity, wettability, etc. Right? Use different methods. Then this one is proposed by my group. That's not a typical way to change a fluid property. As I mentioned already, in order to generate droplets, we need two fluids dislike with each other, right? But if you wish to generate droplets, that's water droplets inside the water, water like water, right? They are same guys, right? Then you cannot generate droplets. then why not you do this? That's one kind of water, that's another kind of water, right? In between, you push oil in, right? Because this water dislikes this oil, then generate this red color of oil droplets. But at the same time, you push this water in. These droplets serve as a chopper that will chop this stream of water into droplets, right? That because oil and water density different as you go to downstream. Then let's see, light one goes to over here, heavy one goes to over here. You separate your oil droplets and water droplets. Then you can generate water droplets inside water. Right, as an engineer, we can play around all those kind of ways to change the flow property. So let's there are some methods people used to control droplets generation by changing flow property. Last way is change your system geometrical parameters, right? Then if you're crazy enough, why not use this kind of geometrical structure, meaning you have one inlet, macro scale kind of channels. You have another one, and the third one with a shape like a square cross sections. The other two, there's a circular one. You put this way, then you put one float going over here, another float going over here, third float going over here. Then you this range, then they will fight with each other. Then after this fighting process, you generate droplets, but this kind of droplets inside we have inner droplets. How many inner droplets you can control? 1, 2, 3, or any number, or one with inner droplets, second one, no. You can do this, right? Then you put, droplets inside the droplets. But if you think that's too simple, but my job or my boss asked me to put droplets inside the droplets, then inside another droplets, why not change your system geometrical configuration into this one? This one means you just add exactly same as this one. Then you will generate droplets inside the droplets, then inside another droplets. You can do this n times, right? So you can control your droplets structures. If you have droplets, you can solidify your droplets into solid format by different ways. Let's, for example, the light or heating or the other ways, cross-linking, etc. We have many ways to solidify the liquid into a solid state. Over here, I show another way to change the system geometrical parameters. For example, you just change this inner channel into two parts. On top part, you put into one float, another part, second kind of a float. Then after flow pass through this, you generate droplets, but inside these droplets, you have two different materials. For drug deliveries, normally we use these functions. If you have a way to put two different materials into one small compartment, you can put more than two, right? Or any number of different materials into same smaller droplets. So that's the ways people used to play around generation of nanoliter droplets, either by using fluid dynamic parameter or fluid properties. or geometrical parameters. So let's move to the second part of my talk, how to control the droplets. Suppose over here you have 1 nanoliter of droplets. You wish to move these droplets to the end of this lecture hall. How to do that? Then think about this very challenging, right? Why challenge? Because the liquid with viscosity never equal 0, never less than 0. That's the second law of thermodynamics. Never believe viscosity can less than 0, can equal 0. If you believe that, that means you don't believe second law of thermodynamics. But unfortunately, in the literature, even some papers in Science and Nature, you're talking about the negative viscosities. Why we got negative viscosity? Mainly 2 reasons. First, there's a definition of viscosity is not definition of viscosity by Newton's law of viscosity. That's the first kind of reason. Second reason, there's a measurement with a so big error such that you get negative viscosity. So never believe negative viscosity, although in the literature many people report they generate negative viscosity. Then if you believe this, then all the liquid will stick on your tool. To handle, by the way, to handle liquid much difficult than handle solid. For solid, suppose I move this bar very easy, right? To handle the water over here, I must use a container, right? Solid tool. But liquid stick on the these tools. Then for bigger amount of liquid, not a big issue. But we're talking about the nanoliter droplets. Suppose just 1 nano droplets use a tool to move to that side, so maybe half of your liquid already stick on your tools. You cannot put out, right? I believe all of us with experience of handling tomato sauce, okay, viscosity relatively high. Then if you put out, then quite a number of tomato sauce left on your bottle, right? So that's one issue. Another issue, to handle the liquid, we need many different functions. For solid, normally just move or rotate, okay, solid. But for the liquid, no fixed shape. Then you need to have functions to move liquid, to merge liquid, to separate, the liquid or disperse your liquid. You need all those kind of functionalities. The third one, sometimes the liquid not so friendly to us. For example, during COVID-19, right? Then if you check, whether this guy get infected or not, then you need to check some bio, fluid which contains, possibly contains virus, not so friendly for us. Suppose you use to do, health test, you test the blood, some blood not so healthy. Then that's another issue, right? So we need to develop different technologies to handle the tiny amount of liquid. But why we need to do this, right? As talking about the challenge, why we need to do this? Then because those kind of liquids or droplets with many applications to handle precisely small amount of liquid, very important for us. At least some put over there. I will not go one by one, but I just use one simple example. For my age, every year polio very good, okay, give me free, annual health test. Then for my age, normally, the doctors need, this 5, stools of my blood, then to do different tests. Then if you use the method I will discuss later in this second part of control or processing of droplets, you just need a very small amount, nano amount. Then you can do all the tests already. So to processing tiny amount of droplets actually very important. Then we need to overcome all those kind of challenges to develop our effective tools. Over last 10 years also, in my group, we developed 3 groups of different tools to processing nanoliter droplets. The first group was just phase separation plus macrofluidics channels. I will discuss a little bit more in detail later. The second method, we just use some natural structures or some structures we produced, okay, to processing the droplets. The third group, I believe, also just use, if you learn, physics, the method we have, that's, in Chinese, 声光电热磁. Or just these 5 different methods. Actually, in science, we understand, sound, light, electricity, magnetic, and, thermal quite well. Okay, comparing this those fields, then we will use, all 5 different methods for processing our small amount of droplets. The first group, as I mentioned, that's phase separation. Phase separation, that's an academic name. But for, public, we'd better use a fatting process. Phase separation is nothing more than fatting. As I mentioned, couple minutes ago, we can put 2 different materials inside one droplet, right? Then why not put 2 materials dislike with each other? You can make 2 materials dislike with each other by many different ways. For example, density different or viscosity different, right? You put 2 materials dislike with each other, then inside one droplet, then naturally we know we don't need to learn physics. Then everyone know they will fight with each other, right? Then that's a typical fighting process showing over here. That's many different such droplets. This is just an enlarged one. Now you can see the typical fighting process like this. This process, normally I discuss this part, I use a divorce process between husband and wife, right? Because they dislike each other, then you put same horse, then what will happen? They just fight with each other. Then if you don't control this fighting process, first those configuration you will find basically in Chinese 头破血流, right? Then finally they separate, divorce, right, into 2. That's a natural process, right? So in social science and natural science, actually fundamental principle exactly same. But you can control this fighting process. For example, if you like this kind of configuration, then solidify this one, become to this solid particle. Then you form your solid particle with the configuration like this. One material distributes inside this, then surrounding this another material. So we can use those kind of simple process to process these droplets. This one is a channel. By the way, I'm not get used to stay over here, okay? But since someone online, I have to stay over here. May I move to that side for this example? For this example, if you crazy enough, by design, you can generate one droplet over here, then second droplet over here, third one over here. By design, you let your second droplet and third droplet merge over here. Then you change the channel cross-section. Then cross-section area is bigger than over here. The first droplet will wait for your second and the third one. Second and the third one already merge into a bigger one over here. Then catch this first one emerge again. Then you can use those kind of simple ways to control your chemical reactions along two dimensions. One is where you got a chemical reaction. For example, over here, second one and the third droplets merge. Then start chemical reaction. And when time maybe over here you design, let's merge over here at the 10 o'clock over here, 1 minute after 10 o'clock, you can precisely control your chemical reactions such that you can generate some materials you wish to generate. So that's first group of technologies we can use to processing our tiny amount of liquid. The second group my computer seems tight. Okay, we got it. We got some, let's see, some natural structure. There's one kind of, plant around us called grasshopper masocco. On this plant surface, we have a very unique structure like this. Now, if you inject one float over here, some same float, sometimes this float go from left to right. I have video over here for the same float. Then this liquid one angle over here have another angle. The angle difference actually control which way the same float go, either from left to right or from right to left. So why not we generate those kind of structures? Then we can dynamically change our two angle difference. We have many different ways to change this two angle difference, right? So I'm not sure where I didn't put the data things for this one. For example, you put some the magnetic particle into your structure that because your structure responds to an external magnetic field, then you can change this two angle difference from time to time, from location to another location. Then you can control your flow of liquid from one place to another place dynamically and locally. So we do have those kind of demonstration, but I didn't put over here. We have mechanical ways to change those kind of structures. So very simple. So this one very simple, but works very well. That's why my students are lucky enough to get paper published in Science a couple years ago. Very simple, right? So we can use those kind of natural structures to do, jobless control. Then another one we use, that's, man-made droplets. Maybe for this one, I use Chinese, okay? Because in Chinese, we have a famous, well-known, the sentence called 竹篮子打水一场空. This with conditions. Not necessarily 竹篮子打水一场空. If your 竹篮子 well designed, bamboo bucket, well designed, you can catch water or any other liquid precisely. After you catch it, then you need to find a way how to release this. After you catch it, very difficult to release, to catch very easily. If your droplet size is small enough, if your blanket, size smaller enough, how small? We call the smaller enough dimensions, just smaller than your liquid capillary length. For example, for water, capillary length roughly 2.5 millimeter. If your, bamboo, kind of blanket smaller than that, definitely you can catch water very precisely. How much you can catch, you can make a calculation very easily. But after you catch it, you need to find a way to release. Suppose you want to move, this water into another place. After move to that place, you need to release, right? Then we found the way to release, basically. This also, quite useful work a couple years ago, 24, 25, I can't remember, published in Nature, chemical engineering. I still feel we are unlucky not get published in Science or Nature. We submitted, but failed. Finally get published in Nature Chemical Engineering. Actually, for this one, we did very comprehensive characterization to find the fundamental principles, how to, catch and release, droplets use open, basically, kind of container. Okay. Then, so we can use all those kind of, man-made structures. Not necessarily use bamboo. You can use any material. Okay. Any material. Okay. To do this. Okay. Okay. I need to wait. Maybe video size too big. Then. Next group, we will use external force field. External force field, including sound, light, electrical, magnetic, and thermal. Right? We use these 5 different ways to control or to process, liquid. I'm not sure. Okay, what's going on over here? Professor Zhang, could you help me to find the issue over here?
Next slide.
Yeah, you already. I'm sorry, my computer may be not so good, but I purchased last year, basically. Maybe my issue is too many videos inside.
Yeah.
That's an issue.
Too many very interesting videos inside it. So
yeah, too many videos. Then
I think we can restart it.
Yeah, let's do that. Any questions during we fix this computer or my issues? Okay. Any questions? Ask me. If you ask me question now, you can pick up any two. Yes.
Very interesting to especially science paper. Depending on the angle, the liquid can go up or go down.
Yes.
From the root to the top.
Yes.
So that must be a balance between gravity or something can help it.
Yeah, but for those kind of field, normally gravity not so important. It's really surface force dominate the process. But we do have gravity input. But those capillary force is already strong enough to overcome gravity resistance.
This capillary.
Yes. Yes, if your structure is small enough, your capillary force is very strong. Okay, if your structure not so small, it needs to be gravity dominant. Yeah.
So I can't find yours. Yeah.
Any other questions? Yes.
About the jetting, you said it's not it's unstable. So what we can do to make it stable?
Yes, for the jetting, basically what I mentioned is this first inertial stage of inner flow stream not stable, but the whole process is stable. Then because this inertial stream is not stable, they will change flow to another one just drops. Okay. But this inertial stage you can control, longer or shorter. Then you can control. How to control? Just play around. There's a three group of parameters: propulsive, dynamic parameters, and geometrical parameters. You can play around. Actually, in that field, my group published people before. Then we let these very large. We use that one to generate problems. Yeah. Yeah, thank you. Yeah. Now I shift to use sound, thermal, light to control or to process of liquid. That's electrical one. Yeah, many groups are working on this field called digital microfluidics. What's this? You got many different electrodes. Then you have very good, controller to control which one charged, which one not charged. Then because of this, naturally you can move the liquid around on this surface. Many people use this method. In my group, we also working on this technology, but the shortage or not so good feature for this digital microfluidics, then you can only control droplets down to a microliter. You cannot use this method to process nanoliter droplets, because if you wish to process the nanoliter droplets, then those electrodes must be very small. But to produce very tiny, size of electrodes still a challenge. No. Another issue you can see, you need, relatively speaking, complicated controller. Okay, so but there's electrical ways. Many groups use this method to process the liquid. What we did, recently we did this work. Okay, that published last year, I believe. Well, that's basically in nature we just play music to our droplets. Then we play different music, okay, than basically sounds. Then those kind of droplets will respond to different music. that will move around. If you have a function move around, you can let two merge or one separate, etc. So that's a video to show. Okay, so this is basically a sound generator that we play, sound to those droplets that we can pattern all those kind of droplets to Hong Kong U. Because why Hong Kong U? Because that's my former students are now still working in Hong Kong U. I left Poly U 3 years ago, Hong Kong U 3 years ago. So they still do this kind of a demonstration to the pattern to Hong Kong U. So you can use this method. This small video shows a thermal method. Basically, we found one kind of material. Okay, this material, if you put your droplets on that surface, the droplets automatically go. You don't need to do anything. Do you believe this? Sometimes depends on your material go along one direction, sometimes two possible directions, sometimes three, or any number of possibilities to move. Okay, that actually physically very simple. Suppose you put a liquid on those kind of surface. Naturally, your liquid will evaporate to the air. Then due to this, then your droplets temperature and the surface temperature will be different. Then if you have a temperature different, then you have a thermal effect to generate some force, because our material is a unique material. If you have a temperature difference, then you have an electrical force. Okay, then to move your droplets around. But it depends on inner structure of your material. You can let droplets move along one direction or two possible direction or three or any number. So that's a thermal method. That over here I show a lot of videos, use a light method. Why this? Because I'm too lazy. I just use some available materials, because for this one, we attend competition, we got award. Then we have lots of material videos to show. Then you just shine a light on the droplets, then you can move your droplets, merge your droplets. Then you can use this method to do soft robots. For this one, just this blue one, just 4 droplets. On top of this 4 droplets, you have a glass plate. On top of a glass plate, you have a payload, something heavier. Then you just use one light shine, you can move this car around. Okay, so that's a demonstration. You can move your droplets vertically. Suppose I do something on this surface. I need to do something on it. I will tell you how to do. Then I just use a laser pointer. Then I can move the droplets from bottom to up. Okay, use this method. Then come to significant part. What I need to do on surface. You need to put 3 layers. Okay, on this surface. First layer is this layer. This layer basically a kind of a material response to light. If a shine light on this layer, will generate a thermal effect. Temperature increase normally. We have many such kind of materials. You just paint this layer over here. Then you put a second layer. Second layer is this material. This material, we have many around us. Paint another material. This material will sensing temperature to convert into electrical kind of force. Then you put a third layer. Third layer very easy. Basically reduce your friction for your liquid move on this surface. Normally people call the liquid repelling kind of a coating. Okay. Then If you do this, then just use the light to control your nanoliter droplets from one place to another place very easily. So that's some technologies we used to do processing of droplets on a surface or in plane. But we do have the other method, mechanical method, to move the droplets from one place to another place three-dimensional. Okay, out plane. Okay, for this one we learn from this below the inside. This inside live on ground or on water. Then they need to move from water to land or back to water from land. Now, when they do this, actually, this part, they have this part in or out. Basically, this part, like water very much, or those part of material dislike water very much, then you can see if this part go out, will interact with water. If in, then this part dislike water will repel. So very simple principle. Then mechanically we just do this. We got a surface contains of two different materials. This kind of material like water, for example, very much. If you want to use this method of process oil, you need design this part like your oil, right? Then I just use water as an example. This net is like water. Then this one, if you go out, will catch your droplet. Then if you let this part in, then this net will repel your liquid, right? Very simple ways. So we use this method for processing our droplets. We can use this simple method to process droplets down to nanoliter, not just microliter. Very assessing. So that's a method we developed before. This one maybe 10 years ago, 9 years ago, published in 2017 in NC, right? So we can use this simple technology to replace all those kind of plastic droplets or tubes. I believe in your lab, you use those kind of plastic tubes. In my lab, definitely I use a lot. Okay. By the way, this one looks very small issues, right? In America, I have a figure that they have, each year, yearly basis, they sell use those kind of 塑料管the 20 billions, okay? That they need 10 billions to process those kind of tubes. You cannot throw away simply. So total market already around roughly 30 millions. So then we can use those kind of technology. All the technology I will discuss later to replace those traditional ways to handle the liquid. I need to check the time. Okay. Another one we can do in or out plane processing. That's a magnetic waves. Now we have those kind of electric, basically open. We just have free frames, okay? Then we put some magnetic particles over here. Those kind of magnetic particles response to an external magnetic field. Then if you want to catch some liquid over here, then you just play around your external magnetic field, move to inside, then you move out, you got the liquid inside your container. Basically, that's an open container. Okay. Then, you can move your liquid, let's to move over here. Then these two liquid will react with each other. Now you can use this method to control your chemical reactions. Now the video over here I show you, so you can use this kind of container catch the bubbles inside your water. Let's see, inside the water you have some air you don't like, want to move out. Then this just catch the air. Then you can move out. Right? You can design those kind of container precisely. Then if you found, in oil you have some water, similarly you use this method to move out, catch just the water, okay, move out, etc. Right? That's a magnetic waves you can use to processing your liquid. Let's move to the last part, some applications, okay? First example, I try to show you just generate macro particles, okay? Macro particles meaning the particle diameter in the range of a few micrometer to a few hundred micrometer. Those kind of particles are very useful, okay? But we need to generate particles shape exactly spherical shape and the size uniform. This one very useful for generate chips. Okay, during generation of chips, they have one process make two plates parallel with each other, but the distance between these two just a micrometer. They just use macro particles to support top one on the bottom one. Then they need a particle exactly spherical and particle size exactly same. So when we do this, actually, in Chinese, that's 我们国家被卡脖子的35项技术的第25项。If you punch, then this one we need to buy, okay, purchase those kind of particles mainly from Japan. Okay, then for the Japan, somehow they have a very good separation for different kind of particles. Then they can get the particle spherical and the size, relatively speaking, uniform. The difference between size, they can make a CV value less than 5%. 5%, roughly speaking, not exactly. If they tell you there's a particle 100 micrometer, the biggest, that's 102 micrometer. The smallest, that's 95 micrometer. But use our method, you already know, droplets just solidify droplets into a particle. Then we can generate our particle exactly spherical by second law of thermodynamics. Natural shape of droplets spherical. If you try to use make your droplets non-spherical, you need to do something. For example, I use, in my group, we use phase separation to make a particle non-spherical. But for this applications, we need a spherical one. Naturally, that's a spherical one. Then, we generate droplets one by one under the same conditions. So we don't need to do anything after solidification. Then we can get a CV value less than 3% better than Japanese product. Okay. Now, when we do this, we try to use this for the biomedical applications. Basically, help a medical doctor to cure, the liver cancers. Suppose this unlucky block the blood into those four very bad, the tumors. Then we need particles, the macro particles. Then we need a spherical one, right? Then also for this application, we need to put drugs inside. Now in the hospital, they just put particles inside the solution of some drugs. The medical doctors just pick up, those kind of droplets inside, drug solutions, then inject into the patient's body. By this way, the drug, loading efficiency normally less than 30%. Only on the surface of a solid particle, they have some drugs. Then if that's a way to load the drugs, then, your release of drugs are not controllable, okay? But our way, we can put all the drugs you need inside the droplets, then we solidify the droplets. So our drug loading efficiency, that's 100% actually. Then we can do the control release. So that's one simple application by using those kind of nanoliter droplets, right? Simply solidify. We can get very uniform spherical droplets, right? Inside the droplets, we can put into anything we wish to input. That's a second example. Recently, we produce, kind of a new magnets. For magnets, we know that we have S-pole, N-pole, right? For example, if you take this bar as a magnet, that's N or S, or this N or S, right? Suppose on this surface, you wish this point N, this point S, another point N again or S again, you give me your requirement, jaw pattern. Then with this macrofluidics or droplets method, we can generate. So that's the process showing over here. Basically, originally that's droplets. Okay, droplets. Then, but this kind of liquid can change phase, depends on temperature, right? Suppose you generate those droplets at a temperature, let's say 40 degrees C, that's a liquid format. After you generate, put into a natural environment, that's a solid phase. Then, but within these droplets, we put into some magnetic particles, right? Then, after you do this, then you use a laser or any kind of ways to heat, let's see, just this one. Then this one become a liquid. Liquid, then use external, magnetic field for distribution of magnetic particle over here, just one pixel over here. Then this, let's say, A over here. Then you do for this one, A over there, or S over here. Then you can use this method to generate new magnets. But now, so far, we can do only resolution down to, 100 micrometer. If you wish to generate your magnet, let's say, one is A, another is S pole, the distance less than 100 micrometer, I cannot do at this moment. Okay, resolution around 100 micrometer. If you imagine you have a magnet, on those kind of resolution, you can play around the distribution of N pole and S pole. You can do a lot of things. Okay. A lot of things that we do demonstration. For example, we use this to open the door, close the door, etc. Then also our magnet is in terms of fibrous, okay, also soft then you can put, in different shape, or then you have another way to play around the pattern of N and S pole distribution with quite potential different applications. So that's, second example, we can use those kind of jobless to do. The third one, we can use a jobless as a marker reactor such that we can control our, reaction inside this small reactors precisely on both dimensions, time and space, such that we generate some unique kind of structures. Those kind of structures are very unique, such that inside those kind of materials, heat transfer process is a new type of heat transfer called heat transfer by thermal waves and resonance. For those kind of heat transfer driving force is not temperature difference. It's a cross-coupling among different processes. Then put this story short, in engineering science, you can have a new material to transfer heat without any temperature difference. If you do this by using definition of thermal conductivity, then your thermal conductivity equal infinity. If your thermal conductivity equal infinity, that's real superconductor. But I can tell you scientifically, for this new type of heat transfer, which we call the, heat transfer with the thermal waves, we cannot use thermal conductivity anymore. But for engineers, we normally use thermal conductivity to characterize the strength of material in transfer heat. We just use this traditional way to define our conductivity for this type of new heat transfer process. That's conductivity value equal infinity. Believe me, human being cannot get anything equal infinity, right? Only God can do that. Okay, right? So people search for the superconductivity. Basically, ways to get conductivity equal infinity. Normally, they do this through material ways. Material ways meaning change material structure or material compositions to make conductivity value very high. Now, normally people can get superconductivity features at a very low temperature. The temperature down to few kelvins. Few kelvins meaning temperature around minus 270 or 73 degrees C. So, but why not use this method to rely to get performance equivalent to the superconductor? Okay, just realize to achieve a new heat transfer process. After we have this material, we can do heating or cooling in different way. For example, today outside, how much temperature? 36, let's put that way. Now we need to open our air conditioner to keep this room temperature around 25 degrees C, right? Such that we can discuss very small, jobless over here. For air conditioner, we need electricity, right? By using this method, we don't need air conditioner. We just, place the lines inside this line with our material. We call the superconducting material. Then outside any material, normally people call the insulation material. For supply electricity, we also do this, right? For the line to supply electricity inside, that's a copper, right? Copper with a very high conductivity value for both thermal and electrical. Okay, Then outside we have the material to cover this carbon, that's electrical insulator. Similarly, for this thermal one, then inside there's a superconducting material. Then outside you need to cover with the material insulation heat transfer process, right? Then you let one side put into seawater, no matter how far away from sea. The seawater, let's say temperature 15 degrees C. Since this kind of heat transfer process can transfer heat without temperature difference, if your seawater is 15 degrees C along this line everywhere, 15 degrees C, then we put line inside this room, right? 36 degrees C. Air will automatically heat this 15 degrees C, the line by normal heat transfer process. Finally, this energy goes to seawater. Seawater, so many, right? Then even you give some of amount of energy to seawater, seawater temperature does not change. Still, at least does not change much, still around 15 degrees C. Now you can use this, just design how many lines put this room. Then you can get your room temperature down to, let's say, 25 degrees C, right? That's cooling. For the heating, same way. Another side just put, let's say, high temperature place, maybe somewhere down ground with some hot water, 70 degrees C for now. You just move to this room, 70 degrees C, the line will heat your air, okay, right? So that's, the superconductor, and fortunately, you can see we generate those kind of material by this way very slow, then the price too high. Basically, that's a challenge we need to work on to overcome. Okay, so last example, I try to show you to use those kind of gel plate to generate some functionalities we wish to get, just generate some materials dislike all the stuff. Okay, suppose on this surface of the table, you worry about some virus or bacteria, right? In particular, during COVID-19, I saw many girls in particular use, the paper, okay, to open the door or, all the surfaces. Why not we paint or coat this surface with some material dislike, all the liquids? Then basically on this surface, very likely no any bacteria, no any virus on that. Then we need to produce those kind of materials. Also, sometimes we need this material, in our kitchen. Then we have butane wok, I believe people know. Then, we wish to use that kind of pot, okay, to cook. Then for our clothes, then if our clothes may be both out surface and inner surface, we coat something, then dislike all the materials, then we don't need to wash our clothes, right? We don't need a wash machine anymore. So we need kind of those kind of applications. Then also for our car, we need, for traditional car, we need to use less oil to travel long distance. For electrical car, we wish to use, less electricity to travel long distance. Then why not we paint our outer surface such that we can reduce friction between our car and the air. For the shape, Similarly, we wish reduce friction between shape inside the water and the water. Then we can save energy. So we wish to get some structures or functionalities dislike all the materials. Then basically we have two ways to achieve those kind of functionalities. One is by chemical method. Chemical method very easy. Okay, you just put, let's say, put your clothes inside kind of solution of kind of drug, okay, or chemicals. Then after you put out, then your clothes become dislike water, dislike oil, etc. Then you can do the washing of your clothes in different way. You don't need a washing machine, but put your clothes inside a water tank or oil tank. After put out, become clear. So that's another way to wash. Okay, when I use, don't need wash. You must put into water or oil or tank, similar as this material. Okay, then that's what we wish to get. But traditionally we use a chemical method. Chemical method, very simple to apply, but we have an issue, not so friendly for us. For example, 不粘锅, they all got that functionality by chemical method. Then for all my good friends, I always told them, use 不粘锅, non-sticky, okay, pot, as less as possible. Okay, then because they have they use some chemicals not so good for us. Okay, then another way to get this kind of functionality is by using structure. By using structure physically, very simple. If on a surface you have some material wish to touch your surface, if naturally your structure design such way you have a vertical force to push this material away, then you can achieve same functionality as you can achieve by chemical ways, right? Then we just try to generate those kind of structures. So for my group, normally we use a second method. What kind of structure we should produce in order to have this simple mechanical force vertical to the surface? Then everyone know. Now, there's a structure on this inside spring tail. Spring tail in Chinese, 跳蚤. Okay, now maybe our living condition much better than 50 years ago. And these insects around us are not so unfair. But 50 years ago, I can tell you, when I study at university, most of my classmates, including me, with those kind of insects, because at that period, our living condition very bad. Okay, we don't have a place to take a shower. Normally, the 2 weeks I take a shower once. Okay, you can imagine. Okay, that's our life 50 years ago. So on this inside the surface, we have a structure. Academically, we call the re-entry structure. Then if you have this re-entry structure when the liquid oil or water touch this structure, naturally have a vertical component of force to push your water or oil away. But how to generate this? You need a macro and nano structure. If your structure is so big, the water droplets this size of water naturally go to your surface, right? Your structure must be smaller enough. Normally, the structure dimension in the micrometer range or nanometer range. How to generate? You can use, top-down or bottom-up traditional method to generate nano or macro structures. But if you use those methods, you cannot generate those kind of re-entry structure. Then we use jobless to generate. Use jobless to generate basically this. We generate jobless. Then we put jobless. Let's say, suppose you reach this surface with this function. We put jobless. I just use one example. All your jobless inside water you put over here. Then inside your water you put some polymers. Okay, inside. Then those polymers, after you do this, your water will evaporate. You can control this evaporation process by heating. For example, you heat, then evaporation process will become stronger. Naturally, we'll have a natural evaporation process. As your water evaporation, inside the water, you have a polymer will cause leak. Then to form some solid material inside the water. During this whole process, all your droplets will change shape. Then you control this evaporation process. And finally, at one point, your all water become a vapor to the air. No water anymore. Then your water phase become to a solid phase. That's a poly liquid. Now you got this solid phase. But on this solid phase, you have oil droplets. Then this oil droplets occupy some space, just holes. This hole, just a re-entry structure. Then you just throw away your oil droplets. So you have many ways to throw away or move your droplets. Then finally, you got on this desk, you have a solid surface. Within solid surface, you have re-entry structures, just the holes. Then, many different holes. Then, this surface will repel all the different liquids. Okay. Now, that's what we did, initially by using this jobless directly, basically jobless assembly, okay, process. Then in last few years, we continue working on this field. Then we got, actually re-entering 3 times, triple re-entering structure, such that our structure dislike all the material, including gas, liquid, solid. Then we do demonstration over here. That's a tomato sauce. Okay, the glass, bottles. After we treat it, all the the tomato sauce can put out very easily. Otherwise, you left some tomato sauce on the surface of your container. So this one we just submitted, okay, in the process of review. We also found, patent application. Now, hopefully, we are lucky enough to get our work published in a journal we wish to publish. So that's, the fourth example. I try to show you application of all those kind of nanoliter droplets. Last page should be summary of my talk. Basically, I wish to use this opportunity to convince you we can do precision generation of nanoliter droplets by changing system geometrical parameters, fluid properties, and flow rate. Then we can processing those kind of tiny amount of liquid by using phase separation, macro channels, natural or engineered surface structures, sound, light, thermal, magnetic waves, etc. Then today I just use 4 examples to show you some applications for those kind of droplets, including macro particles, magnets, new type of magnets, superconductor, and liquid repelling coating. Thank you very much for your attention.
Thank you very much for the Professor Wang, very insightful and very interesting talk today. So if you can continue to ask the questions concerning the droplets field. Okay, anyone, any question from here?
Yes. How to generate or how to
Restore the droplets.
Restore. For the droplets, okay, naturally after a while will disappear. Okay. Normally, if you want to keep a droplet for a longer time, you use separating, okay, for keep droplets. But you can solidify your droplets. Then you got a solid format droplet you keep time. Okay. Normally for restore or keep droplets, then using droplets format, we put some chemicals inside the continuous phase, normally continuous phase. Suppose you have oil droplets inside water, and chemicals are normally called separating. We have different separating. There is a kind of products made by people working on chemistry. We just use. But for our applications, normally we solid change solid form. Yeah. Yeah. You have a version. Yeah.
Okay. Anyone else?
Professor Wang, I want to know the manipulation of the solid is easier. Why do we change the liquid to the solid and manipulate the solid and then transfer to the liquid?
That's a good idea. Now, why not just solidify your nanoliter droplets? Then we move around. Definitely do that. But if you do that, you have a new challenge. The new challenge I can say is as follows. Then, solidification of a large amount of liquid, relatively speaking, easier. But solidification and desolidification of liquid at nanoliter scale also not that simple. Yeah, think about how to suppose you use a thermal method to solidify or desolidify your liquid. Then how to have a system precisely point your tiny amount of liquid. Also, sometimes you can't see, but our eyes cannot see. So with some technical issue, but that's a good idea. So that's why, I need to do this talk many times to get a new idea. I never thought about that idea. Maybe someday, I don't know whether you wish to my group, you do this. The possibility you can publish a paper maybe in Science or Nature, right? So really good idea, but we need to resolve a new energy. Maybe for some applications more effective. Today I didn't discuss robotics. Actually, my group also working on robotics. There's a macro, soft robotics. We have a difficulty to control our droplets or macro soft droplets inside the patient's body. Then maybe your way maybe can help us to resolve some issues. Okay, why I didn't discuss those kind of examples? Although we did publish the paper, quite a number of papers, but we haven't reached that stage yet. But the goal, we try to help a medical doctor to bring the material into the patient's body, or bring out some material medical doctor don't wish inside the patient's body out. Then that's why we're working on those kind of macro and soft, robotics. But for that one, we have a difficulty to control our droplets inside the patient body. Maybe your way maybe can help us to resolve some issues. First, solidify, then much easier to control than desolidify. Okay, yeah, let me think about in future. Maybe we can use that. Yeah, great.
So I have a question for your very interesting presentation. Actually, I'm wondering the several manipulation technology you have demonstrated. Soft, like whether the light induced the manipulation or was the pen light, you have the characterize, you have the code design a specific structure at the end of the pen light, the structure. You can use it to move the nanometer droplets. I'm wondering if it can be used to manipulate the droplets with high viscosity for some non-Newton the liquids.
In principle, yes, really good questions. In principle, those kind of techniques can handle, a liquid with high viscosity or non-Newtonian liquids. But the issue is for the liquid with a high viscosity, the resistance between liquid and the surface much higher than the liquid with a lower value of viscosity, right? Then we need to generate generate stronger force to move. Okay, then you use a stronger light source, for example. Then you change, suppose you use acoustic waves, you change your acoustic wave or frequency or magnitude. Okay, you can do that to generate, stronger force, or use multiple light, streams instead of just a single ones. Okay, that's one way. Another way, you reduce the friction between your liquid and the surface. On top of surface, normally we put some liquid repelling coatings or materials. Then such that we can reduce, the friction. Although your force not that strong, if your friction very small, you still can do this processing of liquid. We can, in principle, we can do. Okay. For example, for the example, I didn't go into the detail for the tomato sauce and peanut butters, viscosity very high. Then, we put into a bottom, or naturally we do this, then they will follow away naturally. The natural force, we use gravitational force for demonstration, but we can use a force strong enough to move those kind of liquid with a very high value of viscosity or non-Newtonian fluids.
Its movement is relatively low than the lower viscosity liquid if you try to move it.
Yeah, if those kind of technologies move to really goes to the market, we need to the installations for the light. We definitely we need multiple stream of light instead of just a laser pointer to do that.
Yeah, thank you.
Yeah, I believe should be okay. We do have a demonstration with a high viscosity fluid, but I can't remember that viscosity value already very high. We do demonstration already there. In principle, should be okay. Yeah.
Any question here?
Yes.
Everyone wants I think. Okay, go ahead.
Yes, go ahead. Talk about there's a technology to make the chocolate comes in small chocolates.
You need big chocolates catch. Small chocolates or small chocolates catch
They catch small. I think maybe two chocolates have to have different prosperities, such as oil and water. Then we can put some things like medicine in different layers. I mean we can put some hydrophobic in oil and hydrophobic in water.
Okay.
And is there any application like this in biomedical?
Medical. Okay. Yeah. Maybe I didn't catch your question completely. I tried to answer. First, you are right. The basically big droplets eat small droplets. Why this? That's the second law. Basically, small droplets unit volume of basis with a big surface area, that surface energy is bigger. Then naturally process should be small droplets better to form bigger one because they have enough surface energy release to power this merging process. That's very good. So you mentioned smaller become bigger one naturally. Okay, by second law of small atoms definitely that's right. Okay. Then I guess you wish to ask me what kind of application. For example, your job is itself was is hydrophilic of hydroponic. Maybe you use oil basically hydrophilic because oil is not water, right? That water hydrophilic. Okay, hydrophilic. So suppose you have those kind of droplet system or what kind of biomedical applications that depends on what kind of oil you use. Okay, then we have many different oils. So let's say we use, corn or the peanut butter, those kind of natural oil that we can put into our animal, even our body itself, no problem at all. But within those kind of oil droplets, you need to put in some materials, we wish put into our biological system. So let's say some nutrition. Okay, we wish to put into the droplet. For this kind of technology, it's very easy to put something into our droplets. I show already. There are some nutrition or some drugs or some whatever you name into the droplets. Then somehow we make. Let's say maybe I would say I'm from Shandong. I know I believe you also know. Shandong have Rezhou, right? Now Rezhou very expensive. Very expensive. Suppose you purchase Rezhou that normally you sell it. Okay, Chinese yuan, right? For let's say 2 or 3 bucks. Okay, that for that one, why not? We use liquid format for Rezhou, right? Then we put those Rezhou, since it's so expensive, you wish those kind of materials digest by the people infected, put into droplets, but you control your droplets surface. On your droplets surface, you have holes. You can make holes. I didn't discuss that part of work we did. Okay, we can play around the droplets surface. Then you control your Rezhou's release into the people's body, because you can inject into a people's body. Then instead use a traditional way to shoot those kind of expensive kind of food. We call them food or nutrition food. Then for that one, you can use medical field. Today I didn't discuss another one application called control drug delivery. Actually, for that one, inside the water, we put some nanoparticles. Finally, nanoparticle form a kind of a shell. Inside this shell, we have different drugs. Then we control that shell's structure. Then to control whether your drugs goes to, let's say, this position or that position only. If we inject drugs into our body, this drug will go everywhere. Our body. Suppose you wish just drugs go to this place because this place with some issues. You don't wish drugs release to our brain, right? Then how to do that? We can use those kind of droplets. Unfortunately, today I move that example away because I think it's still far away from real applications. Then we do have different possible applications in biomedical field. But I'm not so familiar with the biomedical field. Okay, I believe you know more than me. When I studied, at high school, even university, I not have a chance to take biology. That course only up to 203. I attached to the Duke University. I attached Duke University for 8 months. At that time, that's after my graduation from university, maybe already 20 years or 30 years. I start to learn biology, biology. So I don't know much about biology, but I believe I should have quite a number of applications in biological field. But I need to work with you guys, okay, to find real applications. Okay. Yeah, I give you this promise. Okay. Yeah.
So maybe ask the audience from online if they have any questions. Hi, everyone online. Do you have any questions for Professor Wang's presentation? Any question? Okay. So let's thank Professor Wang again.
Thank you.